China's spooky satellite just rewrote physics. Back in the 20th century, Albert Einstein, one of the greatest minds in history, was haunted by a ghost. It was a phantom that threatened to completely unravel our understanding of the universe. He famously called it spooky action at a distance. This was his skeptical take on one of the strangest ideas to ever come out of physics: quantum entanglement. It's the idea that two particles, no matter how far apart, could be mysteriously linked, their fates intertwined in a way that seems to break the cosmic speed limit, the speed of light. For decades, this spookiness was just a heated debate, a paradox that brilliant people, Einstein included, thought must be a mistake, a sign of a deeper reality we just weren't seeing yet. Then, in 2016, a satellite launched silently into orbit and completely shattered that debate. It took Einstein's spooky action and cranked it up to a scale nobody had ever dreamed of, beaming entangled particles over 1,000 kilometers. This wasn't just some record-breaking experiment. It was an event that proved quantum mechanics works on a scale we previously couldn't imagine. In doing so, it fired the starting pistol on a global race to build a totally new kind of internet, one that's fundamentally unhackable. This is the story of Mischius, the Chinese satellite that took a ghost story from physics and turned it into the foundation for our future. Section 1. The spooky heart of quantum physics. So, to really get what Mischius did, we have to wrestle with that same spooky idea that bugged Einstein so much. It all boils down to a property of quantum particles called spin. You can pretty much think of spin as a tiny internal compass needle. But here's where it gets weird. Quantum mechanics says that until you actually measure it, a particle doesn't have a set spin direction. It's just sitting in a fog of possibilities, a state we call superposition, where it's both spin up and spin down at the same time. It's only the act of looking at it that forces it to choose a state. Now imagine a special process that spits out two of these particles at once, sending them flying in opposite directions. This process guarantees their spins will always be perfectly opposite when they're finally measured. So if you measure one particle and find its spin is up, you know, instantly, that its twin, even if it's light years away, has a spin that's down. This connection is what we call quantum entanglement. This is the part Einstein just couldn't stomach. How could measuring one particle instantly change the other one? It seemed like information was traveling faster than light, something his own theory of relativity said was impossible. He argued there had to be some hidden variables, like a secret instruction manual that each particle carried from the start, telling it which way to spin. Think of it like a pair of gloves. If you mail one glove to the moon and open the other one here on Earth to find a right-handed glove, you instantly know the one on the moon is left-handed. No spooky communication needed. The information was always there. For Einstein, the particles had to be like those gloves. But quantum mechanics predicted something even stranger. It said there were no hidden instructions. The particles' fates weren't decided ahead of time. The spookiness was real. For decades, physicists ran experiments to test this, but they all hit the same massive wall: distance. Section 2. The unhackable dream. While physicists were busy debating the nature of reality, engineers and cryptographers saw a massive opportunity hiding inside all that spookiness. Our entire global economy, our governments, our private lives, they all run on secure communication. We usually protect our data with encryption based on really hard math problems that are, for now, too difficult for normal computers to solve. But too difficult isn't the same as impossible. A powerful enough computer, especially a future quantum computer, could potentially crack many of our current encryption methods wide open. Quantum entanglement offered a totally new way to think about security, a method called quantum key distribution, or QKD. Picture two people, Alice and Bob, who need to share a secret key to encrypt their messages. They can use a stream of entangled particles like photons to generate that key. Alice measures her photons, Bob measures his, and here's the magic. The very act of measuring a quantum system changes it. If a spy, let's call her Eve, tries to intercept and measure the photons, Her snooping will disturb their delicate, entangled state. Later, when Alice and Bob compare a small part of their results over a normal phone line, they'll spot mismatches, clear evidence that someone was listening in. If they detect an eavesdropper, they just throw that key away and start over. It's a security system literally built into the laws of physics. It's based on something called the no-cloning theorem, which states you can't make a perfect copy of an unknown quantum state, so Eve can't just copy the key without getting caught. This promises a key that is provably secure, not because of a tough math problem, but because of physical law. It's the recipe for truly unhackable communication. For years, this was the dream. But making it happen was a whole other story. Section 3. The tyranny of distance. For a long time, scientists were proving that quantum entanglement and QKD worked perfectly well in the lab. They sent entangled photons through spools of fiber optic cable, showing the principle was solid. But with every meter of fiber, the signal got weaker. It was a constant fight against decoherence, the quantum state getting destroyed by bumping into things. Photons would get absorbed or scattered by the glass. After a few hundred kilometers, the signal was basically gone, making a global network impossible. Sending the photons through the open air was another idea, but that came with its own set of headaches. Turbulence in the atmosphere, bad weather, and just the sheer difficulty of aiming a laser beam with perfect precision over long distances were huge obstacles. The open-air entanglement record was stuck at about 144 kilometers. The dream of a global quantum network was being choked by the tyranny of distance. How could you connect continents if you couldn't even reliably cross a country? It became obvious that to go further, we had to go higher. The answer wasn't to push through the atmosphere, but to go above it. What we needed was a satellite, a platform in space that could create entangled photons and beam them down to 2 ground stations, hundreds or even thousands of kilometers apart. The vacuum of space is way more forgiving than fiber or thick air. But the technical challenge was insane. It meant building a satellite that could generate incredibly fragile quantum states and aim a laser with unbelievable precision at 2 moving targets on a spinning Earth. Most people thought it was pure science fiction. Section 4. Mises takes the stage. Then, on August 16, 2016, China launched a 600-kilogram satellite named Mises, after an ancient Chinese philosopher. Its official name was QUES, or Quantum Experiments at Space Scale, and its mission was to do something no one had ever done: perform quantum experiments on a truly global scale. For months, the team, led by physicist Pan Jianwei, carefully calibrated the satellite and its ground stations. Then, in 2017, they announced a result that blew the scientific world away. From its orbit 500 kilometers up, Mises created pairs of entangled photons and successfully sent them to 2 different ground observatories in China, one in Dalinka and one in Lijiang. These stations were over 1,200 kilometers apart. It worked. The measurements confirmed the photons were still entangled, their spooky connection perfectly intact, over a distance 10 times bigger than any previous record. It was a massive win for quantum mechanics over huge scales and an incredible feat of engineering. They had beaten the atmospheric interference by creating super-stable optical gear that could hold the link. The experiment proved once and for all that Einstein's hidden variables weren't needed. The spookiness was real, and it worked across the planet. But Mises was just warming up. It went on to demonstrate satellite-to-ground quantum key distribution, also over 1,200 kilometers, creating secure keys thousands of times faster than possible with fiber over that same distance. In a follow-up experiment, they used Mises as a trusted relay to set up the first-ever intercontinental, quantum-secured video conference between China and Austria, a staggering 7,600 kilometers apart. Then they achieved quantum teleportation, beaming the quantum state of a photon from a ground station in Tibet up to the satellite, another crucial piece for a future quantum internet. Section 5. The dawn of the quantum internet. Mises's success wasn't just a cool science experiment, it was a total game changer. It took the idea of a global quantum internet from a far-off dream and turned it into a real engineering project. It proved that satellites are the best path forward for building a worldwide quantum communication network that can link any 2 points on the globe. The shockwaves from MISIUS are still spreading. China has since launched a second, smaller and more efficient quantum satellite named Jinan-1. It has already been used to set up a record-breaking 12,900-kilometer quantum link with South Africa. They've also connected MISIUS to a 2,000-kilometer fiber network on the ground in China, creating the world's first integrated space-to-ground quantum network. The goal is to have a global network running by 2030, offering ultra-secure communication for everything from banking to national security. This has kicked off a new kind of space race. The European Space Agency, the UK, and the US are all fast-tracking their own plans for quantum satellites, because they know that whoever masters this technology will have a huge strategic advantage. We are watching the birth of a new kind of infrastructure, one built not on the classical bits of ones and zeros we use today, but on the wonderfully strange and spooky rules of the quantum world. This quantum internet won't replace our current one for watching cat videos or scrolling social media. Instead, it will work alongside it, adding a whole new layer of unbreakable security for our most important data. MISIUS took one of the most bizarre concepts in all of physics and proved it was real on a scale we've never seen before. It didn't just rewrite a chapter of physics. It started writing the first chapter of a new age of technology, an age of truly secure global communication. It makes you wonder, what other spooky ideas hiding on the fringes of science are just one big breakthrough away from changing our world? Let us know what you think in the comments. From a thought experiment meant to prove a point about absurdity, to a globe-spanning network that promises a new era of security, the story of quantum entanglement is a powerful testament to human curiosity. Einstein called it spooky. Today, we're starting to call it the future. And it's a future that's being built, right now, in the quiet darkness of space.